Hello, BC Calculus students. This is Mr. Johnson, and this is the third video for section 8.7. We're on page 119, and this first part here is just a review of the Taylor Polynomial Series general formula. So we've seen this a few times. I won't get into it really much right now. We saw it in the investigation, and then we've been using it off and on as we've been practicing these problems. So let's go ahead and take a look at number 17. We're going to consider the Taylor polynomial f of x, which is given to us. And we're first asked, what is the first derivative when x is equal to 0? Now we've done some problems like this. We know from the original general form above that we can identify the first derivative in this formula, and we can then compare that particular term to the term that we see in this particular polynomial. Now, in this case, we're dealing with a polynomial that is centered at 0. So I'm just going to write that out really quickly above. Okay, so I've just written out the Maclaurin series. Again, the Maclaurin is centered at 0 always, and then the Taylor series could be centered anywhere. This one's centered at 0, so it could be called the Taylor. It could also be called a Maclaurin series. When we're looking for that first derivative, what we're going to do is compare this term in the general series, which has the first derivative, with the corresponding term in the particular polynomial we're looking at. Again, what we're looking for here is x to the first power. So when we set this up, we have the equation f prime of 0 multiplied by x, that's the general form, equal to the particular term or the corresponding term in our particular polynomial, which is negative x over 2. So if we were just to solve for f prime of 0, we would get negative 1/2. The x's would cancel. So that's our first step. The second step would be to take a look at the second derivative. So now we're going to look at the general form with the second derivative, and we'll look at the corresponding part that has x squared so that we're matching that x squared term. And then this particular formula will be f double prime of 0 times x squared over 2 factorial. So again, that comes from our general form, equal to 2x cubed over 3. That's coming from the particular polynomial. We can cancel the x squareds, and then we can just balance by multiplication. We're going to get f double prime of 0. As we multiply the 2 factorial over, we get 4/3 for our second derivative. Now this process would continue, or could continue, depending on what derivative we want to find. So let's say we make it a little bit more extreme where we're looking at the 10th derivative. Now the general 10th derivative of a Maclaurin or a Taylor centered at 0 would be the 10th derivative of 0 times x to the 10th divided by 10 factorial. And in our particular form, we're now going to look at this generator, and we're going to use n equal to 10. And the reason we're using n equal to 10 is because that would cause us to have an x to the 10th power. So we have negative 1 to the 10th times 10 times x to the 10th divided by 10 plus 1, so divided by 11. And then, of course, we're just going to cancel our x to the 10th, and we'll just multiply the 10 factorial over. And so our 10th derivative at 0 would be 10 factorial times 10 over 11. We'll look at some more of these in some common examples as well. All right, let's take a look at number 18. We have a Taylor polynomial of degree 100, and this function is about 3, which means it's centered at 3, and we want to look for the 30th derivative at 3. So again, this is sort of like that last one where we're looking at sort of an extreme derivative, and we want to look towards the general term of a Taylor centered at 3, which would be the 30th derivative at 3 multiplied by x minus 3 to the 30th power divided by 30 factorial. Now what we're going to focus our attention on is the general term, which is right here. And keep in mind that we must make this power match. We want to make that power equal to 30 in order to match, the terms together, or correspond the terms together. And so that power to be 30 means that x would have to be 15. So we'll write out the specific term based on this polynomial. We have negative 1 to the 15 plus 1, so to the 16th power, multiplied by x minus 3 to the 2 times 15, 30th. That's why we picked 15 for n. And we have then n factorial, so 15 factorial. Now we're simply going to cancel what we need to cancel. We can cancel our x minus 3 to the 30th, and we'll move the 30 factorial over by multiplication, and then we'll get 30 factorial divided by 15 factorial, which is option E. Okay, let's move on to the next page. All right, in this example, number 19, we're going to look at the function f that has derivatives of all orders, and they give us a certain assortment of the function value and a couple derivatives or a few derivatives there. It says let g be the function given by this particular integral. What is the third degree Taylor polynomial for g about 0, so centered at 0? I'm just going to write out the general Taylor really quickly. So here's our Taylor centered at 0, and we'll use the values that we are given in the problem to essentially substitute into this formula. So we have f of 0, we have f prime of 0, we have f double prime of 0, and we have, I think I ran out of, oh, I got blue. We have f triple prime of 0. So what we'll do is just substitute those values in to our formula. So we get f of 0, which is 3, and f prime, so we have negative 4x or minus 4x, plus 2 divided by 2 factorial, so that's just going to give us 1x squared, and then we have f triple prime, which is just 1, so we get plus x cubed over 3 factorial, which is 6. That's going to be our basic Taylor polynomial associated with f of x in this case. Now what we're going to do with that is take that and use it inside the integral. And I'm going to substitute a t in for x because the integration tells me to. So I have the integral from 0 to x of f of t. So I have 3 minus 4 times t plus t squared plus t cubed over 6 and so on dt. Let's go ahead and take the antiderivative of each of these parts. So we have the antiderivative of 3, which would be 3t, minus the antiderivative of 4t, that's 2t squared. This is the power rule that we're working with. Our next antiderivative would be t cubed over 3. And our last one that I have listed at least is t to the 4th over 24. And we're evaluating from 0 to x. So we'll substitute in the upper value of x. So we have 3x minus 2x squared plus x cubed over 3 plus x to the 4th over 24. And we'll subtract, if I was to substitute in 0, we would of course just get 0. Now we're looking for the third degree Taylor, so I ended up listing an extra term, which is fine. It's better to be safe than sorry, I suppose, when it comes to trying to match the multiple choice. But if we look through our answers, we have option C that would match the first 3 terms, or the third degree Taylor polynomial. Okay, let's move on to example 20. For example 20, it's asking for the coefficient of x squared in the Taylor series for sine squared of x about x. There's a couple ways you could do this. We do know what sine of x is, and so we could utilize our definition. I think an easier way possibly is to just think about the general term. So when you're looking at a Taylor series centered at 0, your general term for the x squared coefficient would be basically the second derivative divided by 2 factorial. That's going to be the number multiplied by x squared. So that's the coefficient we're looking for. So I think the fastest way to do this is just simply take the derivative a couple times. So here's our function, sine squared of x. Our derivative is by the power rule, 2 sine of x to the first, multiplied by cosine of x because of the chain rule. The second derivative would be the product rule, so be the derivative of sine, which is cosine, plus the derivative of cosine, which is negative sine. And we're simply looking at the second derivative at 0. Because sine of 0 is 0, this actually just simplifies to 2. And that is being substituted in for that numerator. So when we're searching for the coefficient of x squared, we're searching for f double prime of 0 divided by 2, or 2 factorial. that would give us 2 divided by 2, which is simply just 1. So that's letter or option D. Okay, let's move on to the next example. All right, in example 21, it says the nth derivative of a function at 0 is given by that formula. Which of the following is the Maclaurin series for f? So again, the Maclaurin series is of course centered at 0. This one is certainly centered at 0. We're having to essentially find our function value and a series of derivatives in order to match the answer. So we're going to start with looking at the function itself. This would imply that n is 0. So if you were to plug in 0 for all of the n values, you would get 1/2. And again, what I mean by that is that we're substituting n for our generator here. Okay, so if n was 0 in each of those cases, you would get 1/2. If we look at the derivative, so if n is 1, we do get a negative now. We get 1 plus 1, so we get 2 divided by 1 plus 2, which is 3 times 2, so we get negative 2 over 6. Let's go ahead and simplify that to negative 1/3. F double prime, that means n is 2. We're going to get positive, positive 3 over 16, 4 times 4. We have the third derivative. Not quite sure if we need it, but we might as well because we have those terms out to the third power. So the third derivative would be a negative. We would get 4 in the numerator, and then we would get 3 plus 2 is 5 times 2 cubed. That's going to give us 40. And this would simplify to negative 1/10. Okay, in general, for the Maclaurin series, we have f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared divided by 2 factorial plus f triple prime of 0 times x cubed over 3 factorial. And so we'll just go ahead and substitute all of our values we just found to get our answer. So we have 1/2 minus 1/3 times x plus that's going to be 3 over 16 divided by 2 factorial when we use the second derivative. So that's going to be 3 over 32 x squared. And then we have, for our final one, negative 1/10 divided by 3 factorial. So 1/10 divided by 6, which is going to be 1 over 60 x cubed. And it looks like that is option D. Okay, moving on to example 22. So we have the third degree Taylor for f about 0. Which of the following tables gives the values of f and its first 3 derivatives? So we're kind of going backwards to what we just did in the last problem, or the last couple problems, in fact. We're going to look at the polynomial first, and we're going to identify each of the derivatives, versus in the last problem, we found each of the derivatives, and then we identified the polynomial. We do know right now that f of 0 is 3. We can see that right here in our format. We also are able to determine that the first derivative is at 0 is negative 4. And again, that's going to be right there. Now the next one's a little bit different. When we're looking at 2, remember that's going to be the second derivative at 0 divided by 2 factorial. That's going to be the coefficient in front of x squared. We did that problem, let's see, 2 examples ago that was asked about the coefficient in front of x squared. And then our, let's see, hold on. We need to find f double prime of 0. That would be 4. And then our last one would be, of course, the negative 3 here, and that would be the third derivative at 0 divided by 3 factorial, which is negative 3. Excuse me, and that would tell us that the third derivative at 0 would be equal to negative 3 times 3 factorial, so negative 18. And so if we look at our options, we have option C as our final answer. Okay, let's move on to the next page. All right, example 23. Let f be a function having derivatives of all orders for x greater than 0. So we have that list. Which of the following is the third degree Taylor polynomial for f about 3? So we're going to go through that same process, or at least a similar one that we've talked about, where we have f of 3 plus f prime of 3 times x minus 3. I'll pause and finish the rest of this. All right, so again, this is the general form for that Taylor centered at 3, and we're going to look at just substituting in all of the values for the function and its first three derivatives into the equations. We have the Taylor equal to 2 would be f of 3. The first derivative is a -1, so negative x minus 3, plus the second derivative is 6 times x minus 3 squared divided by 2 factorial, plus 12 for the last one, minus x, or excuse me, times x minus 3 to the third, divided by 3 factorial, which is 6. So if we just simplify down the 6 divided by 2 and the 12 divided by 6 in order to get our final answer, we end up getting option E. Okay, let's move on to 24. It says, let p of x be the fourth degree Taylor polynomial for f about 0. What is the value of f of 4, or the, the fourth derivative at 0? And again, we've done a couple of these already, so it's a little bit of a repeat. Here's our general term, and in this particular case, we're looking for the fourth degree. So we're looking at 6x to the fourth. The x to the fourth can cancel. So we're left with the fourth derivative at 0 equal to 6 times 4 factorial. So that 4 factorial would be 4 times 3 times 2, which is 24 times 6 would give us 144. Okay, example 25 is just a little bit different. We have not talked about this type of concept yet. I should rephrase. We've talked about the first derivative and the second, but we haven't talked about the max and min implication of that. So with cosine of x, if you remember, we've tried to memorize this one. We have our series, and the cosine is even. Might be one nice way to remember that the series is made up of all even exponents. And if we look at what the value of the first derivative is, we notice that there is no term with x to the first, which means that the first derivative must be 0. The third derivative must be 0, the fifth derivative must be 0, the seventh derivative must be 0, because we don't have any of those odd powers there in terms of each of the terms that are kind of missing in this particular series. And so we know the first derivative is 0. The second derivative, I'll go ahead and calculate based on our general term, similar to what we've been doing. Negative x squared over 2 factorial, like that. So in this case, we know that the second derivative at 0 is -1. Now the question asks us for, is there a max or min? They're talking about a relative max or min, or neither when x is 0. So since the first derivative at 0 is 0, we know that's a critical point by definition, and the second derivative at 0 is less than 0, it's -1, then f of x has a relative maximum at x equal to 0 by the second derivative test. And so we've talked a lot about the first derivative test where we look at the sign change of f prime, but the second derivative test actually uses the concept that there is a critical point, so f prime is 0, in addition to testing the sign of f double prime to make sure that we look at concavity related to maximums and minimums. So since this graph is concave down because the second derivative is negative, and since there's a critical point, in other words, f prime is equal to 0, we know that that's going to be a maximum, relative maximum on the graph of f at that point. Okay, let's move to the last page. All right, in this last example, what we're going to do is go through an FRQ, and this is a full FRQ. It's only parts A and B, but it is a 9-point FRQ, and it gives us two different series, one for F and one for G. And the first part is asking us to find the interval of convergence for F. So we're going to use the ratio test to calculate the interval of convergence. And this This part out of the 9 points is worth 5, so it's a pretty large portion of the 9 points in this case. We're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 divided by a sub n, and let it equal or be less than 1. So I have the limit as n goes to infinity, and I'm looking at the series for f. So we have negative 1 to the n plus 1 times the quantity n plus 1 times x to the n times x over n plus 2 times n plus 1 divided by negative 1 to the n times x to the n. And again, we're going to let this equal, or excuse me, be less than 1. As we look at this limit, we can cancel a variety of things. Number one, the negative 1 or positive 1, no matter what that is, we're taking the absolute value, so that's going to just cancel to 1. We have x to the n canceling. We also have the n plus 1 in the numerator and the n plus 1 in the second numerator. So again, I'm looking at these two particular terms in the numerators and the two terms associated with n in the denominators. And when we think about the limit going to infinity, those will all cancel to 1. So what we're left with through this process is the absolute value of x less than 1, or an initial interval of negative 1 to 1. So what we're going to do is test the endpoints to determine whether or not either endpoint converges. So first, let's go ahead and test x is equal to negative 1. And we're using the general term for that series for f. So if we let x equal negative 1, we have the following series. And this could simplify to simply n divided by n plus 1. And that is divergent by the nth term test. And the nth term test simply says that if the limit is not equal to 0, then it's divergent. And this particular limit is equal to 1, so that's divergent. And then we're going to test x is equal to positive 1. And our series then would simply be negative 1 to the n times n over n plus 1. Now, even though this alternates, this is going to also diverge, and it's for the exact same reason that we had in the first one. We're taking the limit of the non-alternating terms, it's equal to 1 and not 0, and therefore it does not decrease to 0. It simply alternates to ultimately a limit of 1, which means it would alternate from 1 to negative 1 to 1 to negative 1, and so on. So our interval that we had found, our initial one, will be the same as our final answer because we did not find that either one of those endpoints was converged, and so therefore it's going to be open both for negative 1 and 1. All right, let's take a look at part B. So for part B, we're going to look at the function y equals f of x minus g of x. It passes through the point 0, negative 1, and we're going to find y prime of 0 and y double prime of 0. So let's go ahead and take a look at the formation of the equation for y first. So again, y is equal to f of x minus g of x. And so what I'm going to do is begin listing some of these terms. So f of x is negative x divided by 2 plus 2x squared divided by 3 minus 3x cubed divided by 4, and so on. And I'm going to subtract g of x, which is 1 minus x divided by 2 factorial, plus x squared over 4 factorial, minus x cubed over 6 factorial, and then so on. Now I want to combine these, which means I need to combine like terms. So for example, the only constant I have is 1. I'm subtracting it, so my first term is negative 1. My next term is going to be the addition of x to the single power. Now notice that we have negative x over 2 minus a negative x over 2, which means that's going to cancel. My next term is x to the second, and so I have 2x squared divided by 3 minus x squared divided by 4 factorial. My next term would be the cubed term, which would be negative 3x cubed over 4 minus x cubed over 6 factorial, and this pattern obviously would continue. Now what I'm concerned with specifically is x to the first power and x to the second power because I'm looking for y prime and y double prime. So I'm going to do just a little bit of simplification, but I'm actually going to disregard that third power just because it's not going to be helpful for the problem. It really won't benefit us. When I'm looking at combining these two terms that have the power of 2 for x, I want to come up with a common denominator. Now, 4 factorial is 24, and so I'm going to take my 2x cubed, or excuse me, 2x squared over 3 and multiply that by 8, both the top and the bottom. So I have 16x squared divided by 24, so I have a common denominator, minus x squared over 24. I'm going to, continue, but again, I don't really care about the third power anymore. I have -1, and then I have plus 15x squared over 24, and it continues. All right, we're looking for specifically y prime of 0. Now notice that the x to the first power canceled, which means that y prime of 0 is 0 because the coefficient in front of x squared is 0, and therefore the first derivative would be 0. And then I have y double prime of 0 divided by 2 factorial times x squared as a general term. However, in this example, it's 15x squared over 24. We did a bunch of these prior to this FRQ in the multiple choice. That would tell me that the second derivative at 0 would be equal to 15 over 12 if I multiply by 2 factorial, which is the same thing as 5 divided by 4. So those are my two derivatives that I'm being asked to find in the problem. Now it asks us to determine whether y has a relative minimum or maximum or neither at x is 0. And so again, this is really similar to that last problem we were working on the previous page. Since y prime of 0 is equal to 0, that is a critical point, in other words, and y double prime of 0 is greater than 0, it's 5/4, y has a relative minimum let's see, relative minimum, sorry, at x is equal to 0 by the second derivative test. And again, remember we talked about how the concavity, in this case, the second derivative is positive, therefore it's the graph of y is concave up. And since we have a critical point at 0 and the graph is concave up, that would then be a relative minimum. And that's the second derivative test. So this part of the FRQ is actually worth 4 points. So part A was worth 5. This is worth 4 for a total of 9. So that's an entire FRQ. And that does it for section 8.7. Thank you.